Good evening, good morning, good afternoon, wherever you are. This is a webinar of Boston Chapter of the IEEE Photonic Society. My name is Keisuke Kojima, Chair of the Boston Chapter of IEEE Photonic Society. Today, we'd like to have a webinar with the title of Evolution of Machine Learning for Photonics Research. The speaker is Dr. Toshiaki Koike-Akino from Mitsubishi Electric Research Labs, MERL. This is a bio of Toshiaki Koike-Akino received a BS degrees in electrical and electronics engineering, MS and PhD degrees in communications and computer engineering from Kyoto University. During 2006 and 10, he was a postdoc researcher at Harvard University and joined MERL in 2010. His research interests include signal processing for data communications, computing and sensing. He received 14 prestigious awards, including a YRP Encouragement Award 2005, the 21st Telecom System Technology Awards, the 2008 Ericsson Young Scientist Award, the IEEE Globecom 2008 Best Paper Award in Wireless Communication Systems, the 24th Telecom System Technology Encouragement Award, and the IEEE Globecom 2009 Best Paper Award in Wireless Communication Symposium. He has more than 260 publications in peer-reviewed journals, conferences, proceedings, more than 250 patent applications, and more than 3,700 citations worldwide. He is an author of 4 book chapters. He serves as a technical program committee member for major conferences, including OFC 2022, and he just became a fellow of Optical, formerly OSA. Okay, Toshi, the floor is yours.
Thank you. I'm going to talk about the evolution of machine learning for photonic research. I'm Toshi, and this work I want to thank for Dr. Kojima, Iwan, Kieran, and other people collaboration at MERL. So thank you for Kojima-san's introductions. I'm working for MERL, Mitsubishi Electric Research Lab, which is located in Cambridge, MA, Massachusetts. And this is, we believe, one of the most academically oriented and open industrial research labs in the world. We are producing more than 100 papers annually. And please check our website. And we have many multidisciplinary fields like artificial intelligence, optimization, control, SP signal processing, and modeling. I'm serving TPC member. Please, TPC member for OFC 2022, please participate in the coming OFC. Okay, I want to talk 4 parts, many parts I have. The first part, I want to just take an overview of trends of machine learning. And second part is machine learning for optical communications. Then third part is machine learning for photonic device design. And the last part is quantum machine learning I want to talk about. First part, machine learning trends. Let's dig into a Gartner hype cycle for emerging technology. And looking back 3 years ago, and you can see that a deep neural network or deep learning was the king of the social expectations. 5G is following something like that. And one later that, actually machine learning or deep learning was gone, unfortunately, and 5G took place of top of social expectations. However, I think deep learning was just rebranded in the name of AI. So the machine learning, deep learning became just the name of AI. This is one trend, I would say. Then the last year, what happens? Still, the AI is kind of important, highest expectation in society. Then I can say one word like generative adversarial network is going up. I'm going to talk about the related talk in our next part. Then current year, what happens? Still, the AI is important. Generative AI is also important. I'm going to talk about this part. And also quantum ML, for the first time, it appears as an emerging technology. And this is also the last part I want to talk. Okay, as you know, machine learning, there are two categories. One is orthodox or legacy or classic machine learning, like support vector machine or logistic regressions. And recently, the deep learning is a more modern machine learning. Actually, deep learning became more popular since 2006 of the paper Hinton published. And he proposed some layer-wise training or massive data training methodologies. Actually, I think there are another drivers like graphic processor unit development or availability became more popular. That was a key driver why the deep learning became more popular afterwards. And also, free Python library are available for everybody, and this is another key driver. And as you know, there are many deep learning architecture like Boltzmann network, belief network, convolutional, and recurrent network. When we see a multimedia signal processing, machine learning did really a good success, as you know. And even ML can surpass a human level performance for some applications like gaming, chess, or Go, for example. And now what happens? And I believe people are just looking for AI for something to apply. I've discovered an interesting trend. For example, I just counted the number of articles in Google Scholar per year. And I just took a keyword search, machine learning plus wireless communication, or deep learning plus wireless communication. As you can see, the deep learning for wireless communications is exponentially growing, like doubling annually. And I call this as Moore's law. And fortunately, I had the one early paper of neural network I proposed in 2004. This is certainly a early stage, but I didn't use deep learning yet. Actually, not only wireless communications, but many different applications we can use deep learning. For example, wireless communication, control, navigation, imaging, biosensing, and device design, and also communication, optical communication. In this talk, I want to focus on optical communication and optical device. When we see a research for photonic applications, actually there are many papers like modulation classification, link quality monitoring, resource allocation, signal detection, end-to-end design, nonlinear compensation, circuit design, and neural processor acceleration, for example. Specifically, I want to focus on the nonlinear compensation in the next part. And also the following part, I want to focus on photonic design. Okay, let's go to the next part. I'm going to pause here if you have any comments or questions.
Yes. If you have any questions, please write in, type in. If not, then let's move to the next session,
Okay.
next part.
Yeah, this is just the trend. And then this is a key part we did for the machine learning application for optical communications. And I think ML just met the optical communication very recently. And again, I counted the number of articles in Google Scholar each year when we search for machine learning plus optical communications and deep learning plus optical communication. And these trends shows that, again, Moore's law tripling annually. And this is a faster than wireless communication case. This was just a doubling. And so the deep learning for optical communications, I think people are more interested in. And actually, fortunately, again, my paper, SPPCom 2014, is one of the earliest paper, I believe, mentioning the deep learning for optical communications. So I want to talk about how the deep learning can be applied to optical communications. Certainly, we have quite a few papers like this. And specifically, we want to focus on nonlinear compensations. As you know, the optical communications, fiber communications, are governed by the nonlinear physics, like nonlinear Schrödinger equation. So the electrical field input in the fiber and the propagation can be nonlinear. How to model this is very difficult, and we usually use split-step Fourier method to simulate. Usually, for data detections, we need to invert back this nonlinear physics. So this is a hard problem. And certainly, if we have a higher power, the achievable capacity may drop like this. So this is the difficulty and the challenge we should resolve. How we can improve the performance in nonlinear regimes. This is very important part. Actually, deep learning is pretty good for a optical communication, I believe, because deep learning is data-driven approach, and we can have massive data in seconds because, for example, terabit class communication in optical fiber, we can easily get many samples easily. So the training deep learning, deep neural network may not be so difficult. But actually, nonlinear equalization is not, deep neural network is not the only way to equalize. As you know, for example, decision feedback equalizer, maximum likelihood sequence equalizer, or Volterra, or digital backpropagation. There are many ways for nonlinear equalizations. Specifically, deep learning is pretty good in my view. There are some joking paradigm shift, I'm saying. ML to ML paradigm shift. What's this? So the maximal likelihood was a very important mathematical model to equalize or detect something. But maximal likelihood detection requires some model to calculate. But under the nonlinear physics, this is pretty difficult because constellation and distortion may not be easily modeled. So we change the paradigm to the data-driven method. And this is ML, machine learning. Specifically, machine learning, deep neural network is pretty good, very analogous to the usual split-step Fourier method. because there are the sequence of linear transform and nonlinear operations. For example, SSFM, we use chromatic dispersion linearity and Carl nonlinearity interleaved. Deep neural network, we use a linear affine transform and nonlinear activation, like sigmoid. So this is very similar. Another interesting part of machine learning training, if we want to minimize, we want to train the neural network, we can use cross entropy loss. And certainly the cross entropy loss is related to the mutual information. And if we want to minimize, for example, binary cross entropy loss, this is a optimizing the lower bound of generalized mutual informations. And GMI is known as a very good measure for the soft decision binary forward correction code. I want to talk about binary versus non-binary cross entropy. This is one of interesting part I'm thinking. And for example, we can use optical receiver signal feeding into the neural network. Then output is some kind of class probability, or then this class probability can be used to calculate the cross entropy loss. This is a very natural way, but there are many different ways, like non-binary softmax cross entropy or binary cross entropy we can choose. Actually, non-binary cross entropy has been used many times, but there is a drawback. If we have higher cardinality, like 1024 quantum dual pole, then the number of non-binary class becomes 2024 doubling square. And this is very difficult to train. Instead, we can use March label binary classification. Then we just need 20 binary classes. Then this can scale up very easily. We can show this. We show the SPPCon paper that if we use binary DNN or non-binary DNN, the performance was comparable if we have low cardinality 4 quantum. But if we have a high cardinality, DP 64 quantum, non-binary cross entropy is not good. And binary cross entropy is the better. So this suggests that the binary cross entropy is pretty good for a high cardinality and scaling well. And also, this is directly used for as a log likelihood ratio to feed into the soft decision input for the fake decoding. And we don't need a LLR conversion after the non-binary classification. That is another benefit. Let's see some neural network equalizer performance for the very standard fiber systems. And specifically, we consider probabilistic amplitude shaping. And because given the shaping, the nonlinear distortion is different. So how we can model using the neural network for such a constellation shaping cases, we want to evaluate. And as you know, there are many different architecture like residual neural network, convolutional, and LSTM. And we just compare some methods. Here, we show the achievable information rate versus reach distance, fiber distance. Here, this is the CNN case, and LSTM and MLP. If we use constellation shaping, we could achieve the 30% reach extensions. And for our case, this case, MLP was best, but it can change for the different systems. Actually, we are more interested in that how we want to use low power equalizations. As you know, the deep learning can be modeled like a affine transform like this. Then affine transform is certainly, there are many multiplication and additions. So we use multiply and add. This is necessary arithmetic operations. However, there is a paper, Deep Shift, deep shift uses affine weights double is just the power of 2. Then we don't need any multiplication anymore. We just need a bit shift, then summation. So the shift plus add. Then we don't need any multiplication. We can reduce the complexity. Actually, we proposed additionally, we call additive power of 2. We just add additional power of 2, and there is u parameter integer and v parameter integer. We optimize u and v to be better. This does not include any multiplication, but doubling just the summations. And how to optimize U and V parameter? We use quantization-aware training methodologies. So as you know, neural network can be trained using forward propagation and backward propagation to calculate the gradient. Then usually forward, backward, then update, like Adam we use. Then if we use static quantization, we usually consider any weights floating point. Then we optimize iteration, multiple epochs. Then afterwards, we quantize. This is a static quantization method. But this is not good because the training is not aware of quantization. And this is quantization aware training, which is the quantization is within the update of each gradient method. Then all weights are basically quantized. So we don't need to use a floating point. And this is particularly very effective. This shows that the MLP equalization, achievable information versus launch power. This pink curve is a floating point case. The neural network are floating point precision. And if we use power of 2 quantization, actually a lot of loss, like 0.33 achievable information rate. However, if we use additive power of 2, we just have twice summations. Then we have no loss. Actually, we have a little bit gain from the floating point. This is pretty good. So we don't need multiplication, and we just need the summations. Still, the neural network is usually very dense and very over-parameterized. So how we can sparsify the trainable parameters is also important. And we use a sparse neural network approach, like we call lottery ticket hypothesis. And this is just we first train the neural network, then after train the weights, we just use this trained weight to rewind the weights and sparsify, then retrain. And this shows interesting phenomenon, LTH, from the 100% density versus some sparsified neural network. If we use this LTH method, the performance can be better. So the sparse neural network can be better than dense neural network. We actually proposed some progressive LTH method. We progressively or sequentially changing the sparse percentage. Then this shows that achievable information versus number of parameters. As you know, for example, if we use many hidden layers, the performance can be better. However, more complex, right? And rather than increasing the neural nodes, hidden nodes, we can increase hidden layers. And this also increases more complexity, but performance can be better like this. And so this shows the trade-off performance and complexity. And we eventually want to have low complexity and high performance. And this shows the trade-off. 3-layer, 4-layer, some hidden nodes, and more layer is not necessarily better than the smaller layer, like this, in the sense of the trade-off. And we want to have this palette front optimization. Then if we use LTH sparse neural network, we can achieve similar performance, but 50% complexity reductions. And also, if we use progressive LTH, actually, from the very dense neural network here, we can sparsify almost 99.7% weights are pruned, but still we can keep the achievable weight more than 10 bits per second. Okay. So, and also we further extended our work for the turbo equalization case. For this case, we actually use neural network for equalization and also feeding back the LDPC decoder's output to improve the performance. And certainly the achievable information rate can be improved by using turbo equalizations. Okay, this is a recap of this part. We showed that the machine learning can be useful for nonlinear optical fiber communications. And we proposed the nonlinear equalization using neural network. And we talked about the data-driven approach as a new paradigm. And specifically, we discussed the binary versus non-binary cross-entropy loss and compared many different DNA architecture. And also, I proposed the zero multiplier sparse neural network. So I believe we are no longer worried about the complexity for neural network, I believe. Then we can sparsify 99% weights without sacrificing the performance. Then we can also improve the performance using the turbo approach. This is quite interesting topic, I believe. I'm going to pause this part to take some questions.
If you have any question, please type in the Q&A tab, or you could also raise your hand. Okay, so here's Shengling Xu raised a hand. Would you like to speak? Just a moment. Let's see how I can make you speakable, or it's not easy to make you speak. Could you type in your question? Okay, so the question, Shengling, from Shengling, adding more layers and nodes can increase the accuracy. Any limit?
Yeah, so actually, for example, here, 3 layer, and if we use more nodes, actually, there is some, how do I say, saturation, and actually going some point, the performance can be slightly degrading. For example, 100 to 200 nodes. Actually, 200 nodes is a little bit worse than 100. And I believe this can be worse and worse. It is because I believe that this is the problem of the over-parameterized neural network. And it's more difficult to converge performance. And same thing for the more layer. I think there are some limit. If we use million layers, of course, that can be worse than some point.
Okay, good. Actually, there are two questions. What is the difference between machine learning and deep learning?
Very good question. So that I think nowadays many people think everything are same, but I think machine learning is a larger group. Then the deep learning is more tier. Then the artificial intelligence is, I think, even larger. So this is like a Venn diagram, I think, but one group and some portion is machine learning as a whole. Then deep learning is a portion of machine learning. For example, as I told you, so there are many machine learning techniques here, like K-means, SVM. But deep learning is one of machine learning techniques. And there are many deep learning methods, but I think mostly we talk about deep neural network.
Thank you very much. Actually, I have one question. Do we need, well, it will also depend on the fiber condition, whether it moves a lot or not, but do you need to update the parameters, weights frequently, quickly, or do you set and keep it for a while?
I think that is also very good questions. In my view, I think we need somehow regular training is required for practical use, I believe, because there are many imperfections of hardware, like thermal stability of transmitter and receiver may change. So we need to keep updating the ways. However, I think there are some methods or some way to keep the constant weights. Then we just use some kind of domain adaptation beforehand or domain transfer at the output part. I think there are some methods to keep the key neural network is constant over the very long period of time.
Okay, thank you. And we have one more question. Slide 30 from Matthew. Slide 35, for a given number of nodes, what is the optimal distribution between width and depth?
I think the question is how we know the best palette front changing the depth and width. Is it correct?
Yes.
And I think this is really tough questions, and I hope there is some theoretical background to find the best point. But for now, I believe practically we just need some brute force method to search for. Yeah, I'm going to talk about the future direction of machine learning. I think this is somehow related.
Okay, thank you very much. Okay, so another question is from Masahiro. Is it essential to choose neurons to remove for the sparse neural network, or can we just reduce neurons randomly?
So I think randomly. So this LTH method is just one of meta learning. So this is we are first training is considering some hypermasking learning. Then given hypermasking, we understood which neuron is not important. Then we can prune. But if we just use random pruning, I believe the performance is terrible. So that we need some kind of strategy to keep some neurons or prune some neurons. I think just a random pruning is not that easy way, a good way. I think just a random dropping is drop out methodology. This is just a ensembling gain we can get only.
Okay, thank you very much. All right, so let's go to the next session.
Okay,
Please.
thank you. The next part is the machine learning for photonic design. And again, I counted Google search number of scholars. And then I found that, again, the Moore's law, but the exponent is different. So the optical communication plus deep learning was tripling. And deep learning plus optical device was 2.4 and slightly slower than the optical communications. However, this is faster than wireless communications. So still there are some interest and some attractive research fields. Okay, we have quite a few papers related for the ML for optical devices. And please check our website. Specifically, we have many literatures we can find using neural network or deep learning for photonic design, like just waveguide nanophotonics, photonic crystal, meta surface design, many papers are there. As you know, as I showed here, currently we can find more than 100 papers per year. So there are many studies are there already. Specifically, I'm going to talk about just 3 categories we are referring. First one is forward neural network modeling. We just use some device topology, then we want to predict the performance. This is forward modeling. And inverse modeling is we want to have some performance, then predict some device topology. And another one is generative model. So we somehow use some generative model. So the spectrum to topology. However, some consistency of inference model we need to impose. First, forward modeling. Let's see how to do this. Actually, if we have neural network, pretty good prediction for the performance, how we want to optimize topology? This is quite difficult because given neural network, we need to still search for the topology. So we may use meta-heuristic optimizer like DBS. Then we use forward neural network to predict the performance. Then we search for the best topology, which has a good performance. And this why this is good? Actually, we can skip the very time-consuming FDTD simulation to really evaluate the performance. So that we can use this forward modeling for designing, but we need some external procedures. And one thing we want to comment here, we can use many architecture, but convolutional neural network was found pretty good for some photonic designs. Then we showed that some generalizability is pretty good for compared to the fully connected neural network. If we use forward regression model to optimize with direct binary search, the gain is illustrated here. We want to minimize some performance loss. Then this is a number of FDTD runs to check this is good or bad. Then we showed that the deep learning assisted heuristic optimizer can be more quickly able to find the better solutions. This is one of the key aspects for the neural network assisting the device design. And more importantly, I think after designing, we could get a pretty good performance, like a very wide band power splitter, for example. And second approach is inverse model. And given some spectrum performance, then we want to produce some device topology. Let's say if we just randomly pick up the training data, then given this training, then we inversely model the neural network to predict the performance. And if we use some active learning to design, we can fill up the the performance of unseen point. And then we also show the experimental fabrication. Here we use applied nano tools fabrication. Then our designed performance was pretty good. Inverse modeling is pretty good. However, there is some problem because this spectrum to topology is not necessarily invertible. I mean, given topology to performance, this may be just a one-way causality. However, given the spectrum, the solution may not be necessarily only unique single solutions. So generative model can resolve such a problem. There are two methodology or philosophy in generative model. One is a very familiar, popular one, generative adversarial network, GAN. And another one is a variational autoencoder. This is considering some generative model attached to the inference model to be most relevant. And certainly, VAE has many different variants. And both philosophy are used for photonic device designs. And let's see the GAN first. So GAN is actually just using some generative model given some random variable. And this should be very similar to a true data space. Then if we have some discriminator to say, oh, this is real or fake, then a generator want to fool this discriminator. Then eventually we can have a pretty good generative model. For example, this is like a currency counterfeiter, like a police versus some bad guy and generating some fake money. If policy is not a very strictly good one, then the fake money can be very realistic. And certainly, for example, GAN is shown pretty successful. For example, this is a fake face image given GAN. However, I cannot conceptually distinguish this is fake or real. And this is pretty successful to create fake images. And also psycho-GAN approach is shown very interesting application like zebra to horse. This kind of flip can be easily generated. Let's move on to the variational autoencoder, second philosophy. This is a non-autoencoder. Neural network feeds some data and we want to reproduce and we have some latent variable. This is just a bottlenecking neural network approach. What is variational autoencoder? Variational autoencoder is actually latent space is sampled from some prior distributions. Then this later part, decoder part is non-generator model because the generated reproduced data sample is very close to a original data spaces. But how to generate this random sample from encoder? This is inference model to be relevant for the generative model. So this is basically consistency training, generator model plus inference model, how we want to optimize both. And we can eventually create a very good generator model. To train, we may use reparameterization trick to be differentiable. And if we use conditional variational autoencoder here, encoder and decoder may take some other label like 5. Then we can create a generative model specifically for 5. However, and then as I mentioned, the decoder part can be used generative model and feeding some desired label, then we can create some image like this. The critical issue of CVAE is actually, even though we put some desired label here, but sometimes the latent variable are not disentangled to this one, then the performance can be degraded and output can be misleading sometimes. So this is a problem. If we use some device topology, this may be a good one. Then if we want to reproduce, then once we train the deep neural network to do the variational autoencoder, we can use this as a generative model. We can use conditional to create some desired topology or desired spectrum here. Actually, we propose adversarial CVAE. Actually, this was originally proposed in brain signal processing, but we quickly applied for the device design. And this was very successful. The key part is latent variable were also censored by some adversarial block. And this is different from adversarial GAN. But adversarial training is not necessarily useful for GAN, but also many different cases like this. And so variational autoencoder can certainly use adversarial training. Then we also proposed extended by using cycle consistency to be better. The good thing of generative model is like this. So given training data, red point, then if we want to generate some particular point, and we can smoothly or seamlessly create many devices easily once we trained. Then we show the adversarial training benefit like this. If we don't use adversarial training for CVAE, the performance can be worse. If we use adversarial CVAE, the performance can be way better. And also cycle consistency can improve the performance, we showed. And then we actually showed some measurement fabricated devices, and actually the performance was pretty good in our preliminary fabrications. One more thing I want to mention is adjoint method is known pretty good for device design, and actually we can combine the adjoint method for deep learning. We proposed this method in ECOC 2021. For example, the blue point is provided by adjoint method. But some points, if we want to optimize some devices arbitrary point using adjoint method, we need a lot of time to optimize. But once we train the training data only using the adjoint method, then we can generate some desired devices, which may be very good small loss. Also, we can sweep many different desired points just using some fraction of points given by the adjoint method. Another point here, adjoint method require many iterations for particularly one device optimization, like 2 hours, more than 2 hours are required. But once neural network are trained using some training data, like 40 minutes, then we can generate a bunch of devices, pretty good devices, just 20 seconds. So let's summarize our part. Next part, this part is, I just introduced forward inverse generative model. Then particularly, we extended the variational autoencoder philosophy for generative model using adversarial training, cycle consistency, and hybrid use of adjoint method. We demonstrated some promising accelerations. Thank you. I have one more part, but I want to take some questions.
Okay. So if you have any questions, please type in. Okay, so Cheng-Li Fu, after the model was established, can it reproduce exact result for training data used, or approximately like curve fitting?
Very good question. So it is known that the neural network is not necessarily remembering everything in the training. So I believe usually we cannot exactly reproduce the training data. However, if we really want to do that, I think there are many different approaches, but usually we cannot.
Any more questions? Okay, so if not, then let's move to the final part, and
Okay.
after that, we can take more questions.
Thank you. So the last part is just like a forward-looking discussion I want to make. Machine learning meets quantum. Why? Actually, deep learning has a critical problem, I believe. And recently, some people showed that training deep neural network may be power inefficient or not eco-friendly. For example, if we train some transformer network and searching for the neural network architecture and keeping training or searching for the good neural network many hours. And there are some paper using such a neural network train, then they estimate that the carbon emissions is 5-fold higher than just a single car lifetime. This is enormous, I believe. This is very critical, particular extreme case, I would say. However, this is certainly showing that the problem in future, if everybody using neural network, deep neural network, then everybody trained a deep neural network using big data, then this actually future society may have a problem to support such a thing. And then one desire is rather than using CPU or GPU or TPU, we may want to use some other modality like quantum computing or DNA computing or something else. Then particularly, I want to talk about quantum computing here. Quantum computing, this was thought about, this can provide the fourth industrial revolutions in the history. It may happen, I don't know. But anyway, there are some government funding increasing, like $1.2 billion for US. Some companies are really producing some real quantum processors already, hardware. IBM, Google, Microsoft, Honeywell, for example. So hardware part is maturing actually. Then also software part is also maturing. For example, free library, many free library are available. And also the real quantum processor can be used in a quantum cloud services like IBM Q or Amazon Bracket. So the society is changing to be ready for quantum. Specifically, 3 weeks ago, IBM released that 127 qubits QPU. This is actually, as they already announced the roadmap. So the 2019, it was only 27 qubits, but last year, 65 qubits. And this year, it became more than 100. And they say that next year, 400. And next year, more than 1,000 qubits are available. So I think hardware part is already matured in many sense. And actually, IBM uses superconducting realizations. However, there are many different ways, like trapped ion and many methods. And specifically, boson sampling and optical, linear optical processor may be one of the interesting things for optical society, I believe. Because, for example, quantum supremacy was reported to be already achieved in some reports. For example, I think Google Teams show that quantum supremacy was achieved by using 53 qubits. It could achieve 200 very difficult jobs. It may require 10,000 years using supercomputer, but it achieves only 200 seconds using QPU. Also, this is more important for Photonic Society. Quantum photon sampling, actually it achieves quantum supremacy, 2 to the 14 faster than the classical computers, they claim. But actually quantum advantage is still questionable or argued for more general applications. Anyway, I just counted for the Google Scholar again, how many quantum machine learning papers are there. Actually, this is also Moore's law, almost doubling every year. And actually, there are many milestones like a variational quantum eigensolver, quantum approximation optimization algorithm, or quantum autoencoder, quantum support vector machine, quantum GAN, quantum graph neural network. There are many approaches are already proposed. Actually, quantum operation may be thought as a kernel, like a Hilbert space kernel operation, like used support vector machine. They show that some quantum circuit can do same way as support vector machine. And another interesting part for us is continuous variable optical quantum processor can represent the classical neural network as it is, and using just interferometer, squeezing, light squeezing, or displacement, or something like that. Then this is one of interesting paper that, okay, neural network can be done using quantum linear photonics. And another paper, interesting thing is universal approximation theorems are also applied for quantum neural network. And this paper showed that using a quantum circuits, and then if we use data re-uploading procedures, then this can correspond to the neural network. And eventually we can get the same way of the wide neuron network, which can approximate any functions. And then this is basically, interestingly, quantum depth is actually neural network width. And quantum width is actually neural network depth. So there are some correspondence here are shown in theory. So it is specifically, if we use many quantum gates, we can approximate better. And if we use many quantum bits, we can approximate better. So both deeper neuron or wider neurons, either way, we have universal approximation property. And another interesting part of quantum machine, actually, quantum processor was a mystery in the past. However, this guy showed that, okay, quantum gates are nothing but can be analytically differentiable. And using some quantum processor inside some classical processing and mix up some trees of the computation, we can back propagate a gradient easily. And they show that they show a parameter shift rule that if we use some kind of differentiation here, then this is exact gradient. So we can analytically calculate gradient using quantum processor. Some paper even show that the convolutional neural network proposed, like image data and mixing up over the quantum circuit, then creates some next channel. Then they showed some kind of random quantum circuit plus convolutional neural network. The performance can be better than nothing, only classical. And there are many, actually, the paradigm is like this. So the quantum circuit is one of neural network, and the neural network has some trainable parameterized functions, right? then we can train the parameter for neural network. That was a deep neural network. Then there is analogy that quantum neural network plus quantum circuit. And quantum circuit is another neural network we can see. For example, quantum circuit has some rotation gates, something like that. We can parameterize the quantum circuit. Then if we train the quantum circuit parameter, then we measure the output. And then externally, we can just train the quantum parameter. Then we hope that the desired output can be obtained. And there are many, many different answers, which is just quantum gates, how we want to build up the quantum neural network. For example, layered gate, alternating gate, quantum tensor network. There are many answers there. Actually, some hypes, actually quantum machine learning is one of key major driver for 6G applications, they think. And actually some expectation of quantum neural network, for example, many parallelism, and also smaller parameter can express exponentially large quantum spaces. So some advantage may be there. And also, I think lower power may be possible in future. Okay, and again, the same plot of the number of articles, but one of interesting finding I thought here is this is a quantum machine learning articles over the year, doubling. I also counted the deep neural network keyword and same exponent and similar exponent, but it is just 6 years behind. This is surprising to me. So let's say 3 years ago, deep neural network was the highest society expectation, right? Then this year, everybody are using deep learning or deep neural network. Okay. Then this plot just suggests that, oh, after 6 years, quantum machine learning is the most popular or maybe highest expectation, maybe. So that I would say after 3 years, probably everybody are using quantum machine learning, maybe. That's my interesting finding. Okay, certainly our group are doing some this way, like we did some quantum machine learning paper for optical communications. Like last year, we proposed high dimensional modulation demodulator using quantum machine. I want to just quickly go through because we are limiting the time. And one of key trend is actually variational quantum circuit. What is variational? Is actually, even though IBM produced a very good quantum processor, but it is still noisy. And quantum noise can affect the performance, like this is ideal simulation, but realistic is pretty bad. So what is variational quantum circuits? Is actually, we may not care about the quantum noise. However, we just care the output of measurement. Then we somehow optimize the quantum parameter only. Then even though neural network may be stochastic or some random noise are there, but still we can just optimize the parameter to be better. And so this can be applied for noisy intermediate scale quantum circuits in the near future, I believe. Okay, and QAOA and variational QE quantum eigensolver are two important algorithms. And okay, specifically, actually, as you know, the Shor's algorithm or Grover's algorithm are very popular for quantum algorithm, exponential or some quantum advantage are there. But those algorithms are actually not useful for the noisy quantum processor because they use the no noise quantum fault tolerant processor they assume. So the instead of such a classical, or I mean the legacy quantum algorithm, this variational quantum algorithm is a more modern way. So we may allow some quantum noise. Then we hope to be best. And QAOA was proposed in 2014. Then they show that this can approach the optimal solutions nearly better than classical algorithm. at that time. Okay, then I use this methodology for the optical demodulation problem. Then let's skip. But anyway, the high dimensional modulation was used for one of the important factor for optical communication because of very good performance. And then, but the problem is to demodulate high dimensional modulation is NP hard, very difficult. So we propose to use quantum machine learning methodology to demodulate the high dimensional modulations. This was my paper in OFC last year. And let's say we can optimize the quantum neural network to be small cross entropy loss to have maximizing generalized mutual information. And then we tested real quantum processor in IBM, and the performance was slightly degraded, but still we just validated. Okay, this is the recap of this part. We just introduced the quantum neural network, quantum machine learning. I think this is one of the future directions, I believe. Then I'm going to summarize the talk, everything. So we had 4 parts. One is trends, and second is optical communication machine learning. Next is photonic device machine learning, and last one is quantum machine learning. Okay. Do you have any questions?
If you have any questions, please write in the Q&A. No? Actually, I have one question. In part 2, you mentioned the sparse neural network is better than the fully connected neural network.
Mm-hmm.
Could you explain why?
So it is very well known that the neural network is usually over-parameterized. So for example, if the neural network has a million parameters, then the training data is just 100 training data. This is basically a lung deficient problem. So it's really difficult to train anyway, right? Intuitively. But still we can do some regularization trick or some method. Then we hope that very good local minimum anyway. So I think LTH sparsification is some kind of similar way. So that we want to solve some problem, but we just hope to be we just use first over parameterized neural network first. Then we shrink the performance to be best fit into some problem. Then the performance can be better. That is basically over parameterization problem.
Okay, thank you very much. Any more questions?
Okay, I want to summarize this one, actually, future of machine learning. I want to say, so the last part is one of such. The quantum machine learning, I believe this may be one of the future direction of machine learning. And I showed such a way. Actually, quantum computing is very, very compatible to photonics and optical society. I think people are very familiar with this quantum photonics anyway. So because photon is just a natural quantum source anyway. So that I think the hurdle is not that high, I believe. And another future direction may be network architecture search. I think the question was like how we want to search for the best palette front, sweeping the different parameter. This is certainly the difficulty. The brute force search is very difficult. And the network architecture NAS approach, which exceeded the car lifetime carbon emission was just using almost the network architecture to find the best. This is a pretty difficult problem anyway. So I think how we want to optimize, how we want to automate the machine learning search or parameterized tuning is one of the important future direction, I believe. The next one is tiny machine learning, like sparsification or small low power something. And another one is photonic acceleration for machine learning. Then also, I think model-based physics-informed neural network may be coming to the important directions. Probably explainability or responsibility is also important. For example, if we train neural network, then we just use the training data sets, but we don't know very different data sets feeding to the same neural network. What is output? We don't know. And how we want to certify the or guarantee the response. Like, for example, if we feed some small perturbation, but neural network go to the like how do I say? I'm sorry, infinite value, for example, then this can be very difficult to use in a real product. I think this is important. Okay, please contact me at this email address for any questions. Thank you.
Okay, thank you very much. Let's wait for 30 seconds more about the questions. If you have any question, please type in right now. Okay. Yes. If not, then again, if you have any questions, please write to toshi.koike@merl.com. And then I'd like to thank the speaker for the very interesting, exciting talk. Thank you very much.
Thank you.